So now you have a new question. So we have this wall, we have these two positive charges. And this wall is right in the middle of these positive charges. And don't worry, I have many such questions. And there is this positive charge. You are told that this is its trajectory. And when it is over here, there will be, of course, the forces acting on this positive charge. What is the direction of the acceleration of the puck at this point? It is A, B, C, or D. The acceleration. I don't want an answer yet. Discuss with your friends. Keep your answer to yourself for the time being. I will ask for the answers. You can ask your friends what they ignore friction, ignore anything else. The only force is the electric force. Ask your neighbors with what answer they have and make sure that you have the same answer. So we have this positive charge puck, and these two positive charged pucks over here, these are fixed. The red ones are fixed. So this green puck follows such a trajectory because these positive charges will exert a force on the red charges exert a force on the green charge. So the question is, when this positive charge passes through this point, what is the direction of the acceleration of this positive charge, of the green charge? Acceleration. Well, this is more of a question on mechanics rather than electricity. Forget these. The important thing are these red charges only. So this green puck just follows this trajectory until when it hits this wall, let's say. But the important thing is what happens here. Okay, how many of you will say A? B? C? D? Okay, why D? Well, you are the only one who says D. Well, even he has an ugly face now. No, he's making faces at your answer. Okay, Newton's second law. What does Newton's second law tells us? Okay, so do you still insist on D? Okay, so everybody says C, so we can pass this one. Now, let's change our question styles. So we have all these conductors. I0 is the inside surface of this inside shell. O1 is the outside of this inside shell. I2 is the inside of this outer shell. O2 is the outside of this outer shell. And then we have a point charge Q, large Q, right at the center. And of course, these are conductors, so it will induce some charges. So the question is, what are the total induced charges in these four surfaces? Orange ones are the conductor. The white spaces are vacuum, they are empty. Think of your answer, then ask your neighbor what's his or her answer. The conductors are neutral. Okay, who think that the answer is 1? 1. 2. 3. 4. Okay, the answer is 1. Now this question first. Then we will have this question. Now first this one. It's the same system of conductors. And we put this point charge over there. The potential at O1, at this point. O1 is the outer surface of the conductor. So basically you are comparing the potential at the outer surface of the inner conductor and the inner surface of the outer conductor. Don't look at this question. We are discussing this one. Only look at this one only. Okay, how many of you think that this is 1? 2, it is lower than at I1. 3, it is the same as I1. Okay, nice. So let's make the groups. 1, 2, and 3. Here is 1. There we have 2. And on the back we have 3. That is 1. Here is we have 2. And there on the back we have 3. Well, I think this one will score a point for me. Okay, why 1? No, we are not looking at I2. We are comparing O1, the outer surface of the inner conductor, and I1, the inner surface of the inner conductor. So you are saying that the positive and negative charges will repel each other, so it will create a potential difference. There will be a force acting on them. There will be a potential difference, and so that the potential at I1 will be larger than O1. Okay, so this is another explanation. Since we have same magnitude of charges in the inner surface than the outer surface, we have more charges on the inner surface. Since we have more charges in the inner surface, the potential at the inner surface will be, no, the potential at O1 is higher than, the potential in the outer surface will be more than the potential at the inner surface. Okay, so the charge per unit surface. So anybody who wants to convince group 1? You ignore them? Okay. So your friend is saying that let's just imagine, okay, they are spherical, but let's just imagine that they are 2 parallel plates. So I have a negative charge on this inner surface, positive charge on the outer surface. So the O1 being the positive charge has a higher potential than the negative plate. So the positive plate should have a larger potential than the negative plate. So that is your friend's answer. Okay, some other answer. No, we didn't discuss that the other day. We had an arbitrary shape, not a spherical shape. Okay, let's listen to the 2. Why 2? Why the potential at O1 is lower than at I1? Okay, this was the thing that I was mentioning you the other day. Not everything goes as the inverse square law. Only almost every property of point charges goes as inverse square law. We had, for example, planes, the electric field was constant. In this one, no. When we come to the answer, you will see that the answer doesn't involve the inverse square law at all. Except then, of course, we will be using the Gauss law. No, I want some more explanations from this group 2. Any other explanations from group 2? Why do you think it's 2? Is the potential at O1 is, okay, why did you change your mind? Okay, what convinced you that the answer was 1? Okay. 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 Okay, so? Okay. Somebody else. Okay, somebody from group 3. Okay, somebody from group 3, why 3? Why they have the same? Why? Can you speak a bit louder? So you are saying the electric field should be 0 inside the conductor? No? The potentials will be equal, so why? So your friend is saying that the charges are not moving, so the potential should be equal. Now, never use formulas without any reasoning. I mean, the formulas are always valid within certain systems, within certain assumptions. 1 over 4 pi epsilon 0, Q over R is valid only for point charges or only for special cases. Why? Why? Why was it that? Why was it flat? Almost. So your friend is saying that since we are talking about the conductor here, the electric field should be 0 inside the conductor. So the work that is done if you move a unit charge from the inner surface to the outer surface is 0. So the potential difference has to be 0 because the electric field is 0 inside the conductor. It's integral as long as you remain within the conductor will again be 0. That is your friend's explanation. No. Okay. Why? Well, you see, the definition of the potential only involves electric fields. It doesn't involve the charges. The charges create the electric fields, but the potential formula depends on the net electric field there. It doesn't depend on anything else. Kind of what? Okay. Which one? Okay, let's apply the... How do you apply the Gauss law? What, which minus sign? Which minus sign? In the definition of the potential, you mean? Okay. 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 No, no, hold on. Which minus sign are you talking about? Which minus sign are you talking about? No, in the Gauss law, we don't have a minus sign. Okay. So first obtain the electric field. What is the electric field that you need to use? You see, E dot, I mean, in calculating the potential difference, you have E dot dl. This can be positive, negative, depending on whether the electric field and dl, they are in the same direction or not. The overall minus sign doesn't tell you that it is a negative number. E dot dl itself can be negative or positive. Now, E dot dl is the magnitudes times cosine of the angle between the two. So E dot dl can always be negative or positive, depending on their directions. So the sign, just saying that, okay, there's an overall minus sign, doesn't tell you the sign. So you have to make some other arguments. Okay, you lost one. So your friend had an argument. Can you disprove his argument? Your friend was saying that since the electric field inside the conductor is 0, E dot dl, your E dot dl, E dot dl, your friend is claiming that E is 0 inside the conductor, so E dot dl is 0, minus E dot dl itself is also 0, so the potential change is 0, and your friend is saying that so the potential at O1 and I1, they are the same. So your friend is saying that inside the conductor, if there is an electric field, the electrons will move around. They will create an additional electric field, and they will continue moving around until this newly created electric field cancels the external electric field, resulting in 0 electric field inside the conductor. On the surface. Well, I mean, so I will answer. He can say that, okay, since it's on the surface, I can choose a path inside the conductor all the time without leaving the conductor. And I can integrate this E dot dl along this along this trajectory, along this path. And since along this path, all the points are inside the conductor, so his arguments will still hold. I mean, the definition of the potential difference is the integral of E dot dl minus. Okay. No. You had already used the Gauss law here to determine the charges. The charge in the inner surface is minus q. So you already know that. You see, we are inside the conductor. If you imagine any surface inside the conductor, the enclosed charge will be 0, because you have plus q charge at the center, minus q charge on the inner surface. They will sum up to give 0.
Yes, but the outer shell of the conductor.
Why? I mean, we are assuming a surface here. We don't care about the outer shell. Why should we care about? No, we are comparing the potential at O1 and I1. We are only in the inner shell. No, yes. You see, we are comparing O1, the outer surface of the inner shell,
Told me about the same thing.
and I1.
When I choose my Gauss surface as its border is O1 and I1.
So these are our surfaces. We have the outer shell, we have the inner
That's
shell,
what I meant with outer shell and the inner shell.
and we have a positive Q over here. You said here we have minus Q, here there's positive Q, minus Q, positive Q.
Yes. May I change the color of just
No, it's now red, black.
This is my first
Okay.
surface.
It is right out of, just out of the outer shell, right?
Yes, and this is my second Gauss surface.
Just inside the inner surface, or just out of the inner surface?
Something else in the inner surface.
I mean, don't take such limiting cases. Either say out of the surface, inner surface.
Let's assume out.
Okay.
It's much easier.
Okay. Now, you are taking S1, let's say, and S2. E dot ds on the S1 surface will be plus Q, no, 0.
S1, yes.
And the integral on the outer surface will be equal to,
Epsilon minus Q.
no, plus Q over epsilon 0. So from here, how do you switch to the potential difference? Now, how do you relate this? These are both true. I mean, your friend is taking a surface just inside my conductor here, plus Q minus Q, the total enclosed charge is 0, and the surface just out of this shell, we have plus Q minus Q plus Q inside this Gauss surface, so the integral is Q over epsilon 0. Now the question is, how do you relate these two facts to the potential difference?
We define the potential as the integral of E dot dl.
Delta V is equal to E dot dl minus. Okay, and now, which electric field is this one? No, I mean, at which point are we calculating this electric field? Electric field will have different values at different points. So which point are we going to use? On the outer surface, on the inner surface, or at which point? Both of them. So you are saying we have to calculate this integral for the outer value of the electric field and for the inner value of the electric field. So, and then take the difference to obtain this delta V. No, okay. So which E is this? So you have already two expressions for two different electric fields, one on the surface S1, one on the surface of S2. Which E is this?
We're going to apply one by one.
What do you mean one by one?
Excuse me?
What do you mean by one by one?
Yes, at first we will use it for the minus Q charge. Plus Q and minus Q charge for the inner circle, inner place. And the second one for the outer place.
And take the difference.
Yes.
Okay, so that's one explanation. So your friend is saying use one for S2, evaluate E dot dl, use one for S1, evaluate E dot dl, and take the difference. That will give you delta V. Any objections? Okay, first of all, let's correct which E is this in this integral. Remember how we define the potential difference, how we define such an integral. We had this point, some point, and we had some other point. And we wanted to calculate the potential difference between these 2 points. First of all, we just chose some arbitrary path connecting these 2 points. Now, we can choose an arbitrary path because we already know that for the electric field, this integral is independent of how you go from one point to the other point. So whichever path you choose, it will have exactly the same value. So you choose some point, some path, whichever one you like. And then you divide this path into very small segments. So let's say at this point, this is our DL. We have a very small segment over there. Right at that point, at where my DL is, I have some electric field. In some direction. And the potential difference between these two endpoints of my very small segment is, let's call it dV, is E dot dl. Here, the electric field is at the point where I have this dl vector, not at some other point. It's at this segment. I'm evaluating the contribution of this segment. I calculate the electric field at that segment, take the minus sign. Take its scalar product with this dl vector right at that segment. Take the minus sign, and that gives me the potential difference. When I want to calculate the contribution of, let's say, this segment, I calculate the dl corresponding to that segment, multiply it with the electric field at that segment, and add the contribution. So in this delta V, the first thing you have to do is choose a path. Which path would you like to choose? And then you have to determine the electric field at every point on that path, so that you can evaluate these contributions from each one of the segments. So it is the E over here is not the E you obtain here. This electric field is the electric field right inside the conductor, which is 0. And this electric field is the electric field right out of the conductor, which will be non-zero, but these two values are not relevant for us. Because first of all, we have to determine a path, and we have to evaluate the path at every point on we have to evaluate the electric field at every point on this path. Now, any other explanations you would like to give in support of your choice of the answer? Now, is this point clear, by the way? Which electric field we are using in this integral? It is the electric field along the path, not just electric field at one point or another point. So if you are calculating the contribution of this segment, you have to calculate the electric field at that segment. So now back to our questions, 1, 2, or 3. Anybody else who wants to defend their answer? Y1, Y2, Y3? No, not necessarily. This is the electric field created by whatever charge you have. Now, in our case, we have this plus Q charge on the outer surface, minus Q charge in the inner surface, plus Q charges on this outer surface, minus Q charge here, plus Q charge over there. All will be affecting the electric field by this means or some other means. So you just calculate the net electric field created by all these charges, not necessarily just the one on the middle. And then this is your electric field, you have to integrate it. Well, you lost 2. They went over there. Okay, why 2? Why do you still think it's 2? I mean, your friend I think he has a nice answer. Your friend is saying that, okay, since I can choose any path connecting the outer surface to the inner surface, any path should give me the same answer. I just choose, let's say, a path that goes from the outer surface to the inner surface and remains always in my metal, always in the conductor. And as we have discussed in electrostatics, inside conductors, the electric field should be 0 everywhere. Electric field is 0 along this path. So E is 0, E dot dl will be 0. Minus 0 is 0. So the potential difference along this path will be 0. Since the potential difference is 0, any point on this path will have the same potential. So the potential in the at O1 will be the same as the potential at I1. Now, does this mean you are convinced the answer is C? Okay. Now we have the next question. This time we are comparing the potential at the outer surface of the outer shell with the inner surface of the inner shell. Remember, in this question we were comparing the outer surface of the inner shell with the inner surface of the inner shell. Now we are comparing the outer surface of the outer shell with the inner surface of the inner shell. I1 is fixed. We are always comparing with I1. In this one it was the O1 and I1. Here we have O2 and I2. I1, sorry, O2 and I1. So which one is larger, which one is lower, which one is higher, or whether they are the same? Okay, let us take the answer. We don't have too much time left. So how many of you think that the answer is 1? The potential at O2 is higher than at I1. Okay, how many of you think that the potential at O2 is lower than at I1? How many of you think that they have the same value, just as in the previous case? Well, if we had more time, I would be making you move around. Why 1? Why do you think the answer is 1? Those who said the answer was 1. So your friend is saying that let's draw our path. So this is our outer shell. This is the inner shell. And your friend is saying, let's start from here and go take a path to the inner shell. Okay? So is this positive or negative? That's basically the question. Or 0. Yes. Okay. So here the electric field is 0. Here the electric field is 0. Because we are talking about conductors. So you are saying that this difference is nothing but the difference between P2 prime and P1 prime. Now why is this, the question is whether this is positive or negative. How can you determine whether this is positive or negative? Okay. So whether it is positive, whether this is positive or negative, how will you relate it to this? You mean here? Here? Here. Okay, why did you start from there? Why? So you evaluated this integral and also this integral and took the difference. Okay, so the answer? Well, let's stick with this one. It will be simpler. Now, first of all, do you agree that the electric field on this inner empty place is pointing outward? Does everybody agree with that? The inner shell. Because we have a positive charge over here, plus Q. If we take a Gauss law over here and assume that the electric field, it will be in the radially outward, it will be in the radial direction because the problem has spherical symmetry. So E dot ds on that Gauss surface will be nothing but 4 pi r squared E. This integral. And the total charge inside the surface is nothing but plus Q. So this will be Q over epsilon 0. And E is 1 over 4 pi epsilon 0 Q over r squared. Now the critical thing is that this is positive. We put some positive charge here. Q is a positive number. So this is positive. Since E is positive, the electric field is pointing radially outward. Now let's look at this path connecting P1 prime and P2 prime. So this is, let's say, our P2 prime. This is our P1 prime. This is the path that I chose. And I'm moving from P2 prime to P1 prime. So I'm moving in this direction. If I divide this segment into very small parts, dl, well, the electric field at the point of dl is also radially out. So this is my electric field at the point of this segment. But this basically means that E dot dl is larger than 0. But if E dot dl is larger than 0, the integral of E dot dl is also larger than 0. But the potential difference is minus this integral. So the potential difference here is minus this integral. So this is delta V is less than 0. So it just means that the potential at the inner surface is smaller than the potential at the outer surface. So let's go back to the answers. Potential at the point O2 is, let's see, higher than the at I1. No, hold on. So, yes, it's the opposite way around, sorry. The potential here is higher than here. I1 is larger than O1, O2. You can also think of it, imagine some positive charge. You are trying to move the positive charge from O2 to I1. You have to do work against the electric field. So you are going to a higher potential. Now, what did we say over here? Okay. E is 0 here, E is 0 here, but E is not 0 here. This is not a conductor. This is empty. No, we are comparing these 2 points. We are comparing this point and this point. So we have to imagine a path that connects these 2 points. So I just assume that I am taking, as I'm going from P1 to P2, okay, I made a mistake over here. My dl is pointing from outer surface to the inner surface, whereas the electric field is in the opposite direction. So E dot dl is negative. This is less than 0. This is less than 0. Delta V is larger than 0. So, okay, this question we will discuss on Tuesday again. Okay, see you on Tuesday.